Before we look at lecture note 2, let me ask you a very quick question. This time series is the real GDP sequence of Korea, of course. Is this series stationary? We learned the concept of stationarity, right? And I emphasize this is a very important concept if you want to build time series model. Do you remember what was the condition for stationarity? We learned something about weak stationarity, right? Or covariance stationarity. It has something to do with mean, expectation, the variance of a random variable, and covariance. Those are constant and doesn't depend upon time. Okay, so that was the condition. Okay, so let's check whether this real GDP is in fact a stationary time series, or if not, it's non-stationary time series, right? So eyeball test. Suppose you have the data starting from first quarter of 90 to, let's say, 2000. If you calculate sample mean using data up to that point, mean is about here, right? Mean is about here. Suppose you extend your data to there. Now you calculate sample mean. Will it be this? This, right? So we can expect that as time goes on, the sample mean will increase, right? Which violates this condition, right? So this series doesn't seem to have sample mean. Okay? Also, if you look at the first half of the data, the covariance or variance, the second one, variance is a measure for the dispersion of this series. So you vary around this region, right? But as you have more data, the fluctuation is from here to there, right? And it appears to increase over time, right? Which violates the second condition, right? So this series, from our eyeball examination, this is not a stationary time series. Okay? So it belongs to non-stationary time series. The lecture note 2 will cover the model known as ARIMA model, which stands for autoregressive integrated moving average. Integration is something like this, calculus, the area, right? Later, let me explain what we mean by integration here. But for the time being, let's ignore this part. Autoregressive part, we've seen that previously, like yt is explained by, let's say, yt minus 1. So that's the regression. And because we are dealing with same y at different legs, so it's autoregression, right? The moving average is something like if you have observations like this, moving average is simply like, for instance, take average of these two, and then average of these two. So take average of these two sequence and record it here, and take average of this and record it here and there, and this sequence is moving average. Okay. So we'll start with the model that has autoregressive part and moving average part. And then later, this part doesn't require any additional modeling. We'll get to that part. But simply, if you have non-stationary time series like this one way to convert this series to a stationary one is this one. This is growth rate of this sequence. So the first step in time series modeling is to examine whether the original sequence is stationary or not. If it's not stationary, then convert it to something stationary. Okay? If we have a GDP sequence, let's say real GDP, a particular quarter, usually you can take natural log. And natural log function is monotonic function. It doesn't change time series property of this one. Just a simple mapping from original data to this space, natural log. Why we take natural log? Well, if you let this sequence as y, if you define sequence y as natural log of GDP, original series, by taking first difference, let's define xt as first difference of this. What is this quantity? This is approximately its growth rate. Okay. So later it'll turn out that even though you want to model GDP to generate forecast, what we deal with in this modeling is this quantity. So suppose you model this one. Suppose you calculated what is this quantity next period. Okay. We know this is a GDP, of course, natural log of GDP. So if you exponentiate this one, and you'll get this GDP back, right? If you have this value at t plus 1, well, you see yt is simply yt minus 1 plus this quantity, right? So if you know the value at t and t plus 1, then you will know the value of yt at t plus 1, right? So that's the way it works. Okay? Integration has something to do with this, and we'll get to that part later. Okay. Okay. So now, then how to model this one? Well, first thing is it appears that there is a mean. Let's say about 1%. This is a quarterly growth rate. So 1% per quarter means if we annualize it, it's 4% a year, right? So GDP has been growing around 4% a year over the years, right? We know that there is a dramatic decline in GDP. Of course, that reflects 97 currency crisis and dramatic decline here. That probably corresponds to the first quarter of 2009. So 2008, around September 2009, 2008, we had a Lehman crisis. So since then, in the following quarter, we have dramatic decline there. So later, we have to make a decision about how to handle this information. Will we treat this one as something like outlier or something that happens recursively? So will this happen again in the future? If you think that's the case, then you have to include this in your modeling. Right? But if you think that, if you consider these two as something very peculiar, outlier, then probably you want to leave this thing out when you model this one, right? So we'll get to that part. Well, if you think it, very plain term, how to generate forecast from here? Well, suppose that stock price, if stock price decreased yesterday, what's going to happen to stock price today? Well, suppose it increased. Suppose you observe that pattern over the period. So when it declined and then bounce back next day. When it bounce back and then next day it falls. We say that's the sort of covariance. On average, two adjacent observations tend to move to the opposite direction, right? So if you calculate covariance between current observation and previous observation, the covariance is going to be, in that case, negative, right? So if that was the case, then obviously your forecast is going to be this one, right? If that was positive, negative, that pattern, right? But usually our eyes can be deceived quite easily. If you change the scale, depending upon whether you shrink this thing or stretching it, the impression is going to be very different. Very different. Okay? So we start with some of the basics so that we can actually calculate those quantity and to see whether we can use those information in the model building here. So this data is the one, you've seen it already. As you all know, GDP is published every quarter, right? Every quarter. This is quarterly data. There's no monthly GDP series. Okay? And also, when we measure business cycle, we work with this one, real GDP, not the nominal one. And also, this appears to be very smooth, right, over time. But actually, if you actually calculate, let's say, what is the real GDP this quarter, Well, there is always kind of pattern that look more like, if I exaggerate, like this type of pattern. Like we started the lowest in the first quarter, in the second quarter, the third quarter, and fourth quarter. You can probably guess why, right? Christmas, a good season, right? And then fall, and so on, right? This sequence is seasonally adjusted. So the Bank of Korea, who is actually collecting this data, applies sort of filter so that when you feed this original sequence, which is not seasonally adjusted, if you feed in that series to the filter, then what you get is something smooth, like this one. So later, I can explain what kind of logic is behind when you try to smooth something, like when you try to seasonally adjust sequence. But here, when you collect your data, you have to check always whether the sequence is seasonally adjusted or not, right? And computing growth rate, we learned it here. This is one way. This is a quarterly growth rate, or approximately this way, right? Then how to calculate annual growth rate? Quarterly growth rate is like 1%. How to calculate annual growth rate? Well, actually, this number that corresponds to a particular quarter, that's a quarterly GDP. So if you add them all, so 4 observations for year, particular year, that's annual GDP, right? So if you have annual GDP, year t minus 1, of course you can calculate annual growth rate, right? Or people tend to calculate like, well, if you compare these two GDP, seasonally not adjusted one, there is a decline in output, right, in the first quarter usually, because we have lunar calendar year, Chinese New Year, so we have a break, shorter days of work, right, in the first quarter. So if you literally interpret these two observations, well, this just reflects a seasonal variation, not really the sluggish economic condition. That's not the case in this case. So what people do is they compare this quantity with the one 4 quarters ago. Okay? So the first quarter is compared with the first quarter previous year. So if you calculate GDP this quarter and first quarter, that will give you annual growth rate, right? Annual growth rate. So calculate growth rate here and here and here. That's another way of calculating annual GDP. Of course, internationally, the standard practice is to report this quantity first, this one, quarterly GDP. and then, if necessary, annualized version in this way. Okay. This graph is a plot of sine curve. So if you are given data up to here, then forecasting sine curve is very easy, right? Because it's quite regular, right? Quite regular. And we say this is deterministic. Deterministic. Time trend. Suppose there is a time trend like this one, straight line. Of course, you can project this one, right? Easily. Because it's deterministic. There's no uncertainty. Right? So the reason why predicting GDP is very difficult is because of that uncertainty, right? So uncertainty is modeled. But before we get there, this exhibit shows that, well, some series like Korea Stock Price Index, KOSPI, well, by now we know that the KOSPI is something like this one, something trendy. So it doesn't have any mean. How many of you own stocks? I don't have one, although I teach, those things, but I don't have one. Well, if stock price, well, KOSPI is around 1950 these days, right? We all hope that sometime it cut through 2,000 and 3,000 and forever, but you never know, right? That's same as saying, well, there is no constant mean. So it's not reverting towards a particular value. It just wander around, right? So your eyeball test on this sequence, well, will it have, let's say, some constant value, average value? Well, may not, right? Right? So in that case, instead of relying on your eyeball examination, we apply sort of statistical test known as unit root test. And we can statistically make statement about whether a particular sequence is stationary as it is or non-stationary as time series. Okay. We'll get to that part. So because we know that the stock price is usually a non-stationary, we work with growth rate. But in finance, we don't say growth rate of KOSPI. We say it's stock return, right? So this stock return is simply log differences of this one. Then it appears that this has constant mean, right? And the variation is within this range. So, the first thing you do when you try to model a particular time series, first thing is to check whether a particular series is non-stationary. If necessary, we convert it to something stationary. This is volumes of trade. It is also known as non-stationary time series. And this one is low difference and appears to be stationary. And also we see it. We take a look at histogram, for instance. using this one as a data, and this bar graph is a histogram. The smooth curve is usually the one that corresponds to normal distribution. So suppose you have a data, as many data like this one. Calculate sample mean and sample variance. And if you know sample mean and variance, and if this data is generated from, let's say, normal distribution is completely specified by two moments, mean and variance, right? So you plug that number in, then this is the curve, known function, normal distribution. So by comparing normal distribution that is implied by first and second moment and actual or empirical distribution, if this data is in fact really drawn from normal distribution, these two has to be very close, right? Very close. But many of our financial time series, when you actually do this type of exercise like this one, usually it is peaked in the center, and usually it has longer tail than normal distribution. See, there is a peak. Statistically, we say this is leptokurtic distribution. This is a peak. So it has usually a higher peak than normal distribution and has a longer tail. You can see it well, but this normal distribution quite quickly converges to zero, but there are several values like this one, right? Those numbers in the tail. Because, well, these are simple descriptive statistics. But by looking at this type of facts, we try to build a model so that your model, if data is in fact generated by a particular model like this one, it has to generate data that look more like this one. But in reality, data look more like this one, right? So your model should also generate this type of data, right? So first thing is, we are not going to worry about, in this modeling, we are not going to worry about this feature. This is a feature we'll be modeling additionally when we talk about volatility model. Okay. So that's the issue we'll cover next after this one. Today, we'll see something like this one or this one. Notation here, autocorrelation function. Autocorrelation suppose you calculate covariance between these two adjacent observations. Okay. Let's call this one as gamma 1. So one period apart. Okay. So if you calculate covariance between xt and t minus k, then gamma of k. Okay. If you let this one be same xt, so xt, then it has to be 0, right? 0. So gamma 0 is by definition the same thing, right? Actually, the covariance is the building block of this modeling. Well, so what it tells you, let's say this is K. Let's say this is positive. So observations K period apart is on average having positive relationship. So if xt minus k increases, then k period later, it tends to increase, right? So if current observation increase, the k period apart, that one is more likely to increase, right? So those covariance structure is going to be used in this modeling. So suppose you calculated, let's say, covariance between observation 1 period apart, 2 period apart, all the way through k. So k is horizontal axis, okay? And the vertical axis, you put these numbers. Okay? So suppose when you calculate that, suppose every covariance is 0 for all k's. That means no relationship whatsoever, right? So knowing the past won't help you much. You try to forecast, right? So that's the dead end. That's the way. That's the end of the story. But if some of these are not 0, then that's some information we can take advantage of in building your model, right? But when you actually calculate this quantity, suppose you multiply xt sequence by 100. So 100 times this and 100 times that. Just scale is blown up, right? And then this quantity is going to increase, right? By this much. So covariance, well, this magnitude is, let's say, 30. Suppose you calculated covariance for this quantity. Well, suppose that turns out to be 30,000. Which one is more strong? Well, covariance 30 and covariance 3,000. Well, 3,000 appears to be, stronger signal, right? Gives stronger signal. But in fact, what we did is we just scaled this one by 100, but not changing any structure here, right? So covariance measure, what I'm trying to say is covariance itself is not scale-free. So when you try to measure whether some observations, k period apart, is in fact strongly tied or not, covariance is not a good measure. Instead, what we do is covariance is scaled by variance. If you calculate this quantity, which we call it as correlation, if these are perfectly correlated, then this number is going to be 1. If these two quantities are moving exactly opposite direction, then it's going to be -1. Okay? If there's no relationship, so covariance is 0, then this quantity is going to be 0. Okay? So it is bounded from -1 to +1, always. And if you move to the end of this range, more strong signal, right? Strong tie between two observations, right? So here, autocorrelation function, this axis is k. Here, horizontal, vertical axis, that's the value this way. So if you plot rho against different k's, then we say this is autocorrelation function. Okay? We'll get to that part shortly. And here, we also look at something called partial autocorrelation. And let me explain what kind of information that those two statistics is telling us. So this is actually the model. The ARIMA model, usually universal notation, the P and then D and Q. So sometimes this model is called PDQ model, some people say. Or the developer, two statisticians, Box and Jenkins. So sometimes we call it a Box-Jenkins model. The basic representation looks more like this one. The notation, this Y is similar to this one, usually. This one. Nabla D, well, D is defined where? D is difference operator. So if D is 1, effectively is taking first difference. So this notation. Right? Of course, we know that from previous slide that because GDP itself is non-stationary, we are taking first difference to make it stationary, right? Sometimes some series may require two differencing this one again to make original sequence stationary. It's very rare, but there could be a case, right? So, but usually most of the economic and financial time series, it requires just one differencing. Okay? But this is general notation. So let's assume D is 1. So taking first difference, which is X in our notation, right? Has this part and that part. And this part, pi of L is a polynomial in L, right? Polynomial in L, right? And L, what is L? Well, L is the lag operator. And it works this way. If you have series Y at T, if you multiply that by L, this operator, effectively it is lagging one period. Okay? Suppose you multiply L again, L squared, right? So this one is YT minus 1. And if you multiply L here, then that one will make this one YT minus 2. Right? So if you multiply L to the power K, it will make this sequence lagging by K period. Okay. L is something that you can add, multiply, and divide. This is the operator. So lag operator. So let's define, let's say, pi 1 through p. Those are parameters of this model. And this parameter, this polynomial, in fact, is governing the dynamics of YT, and of course, first difference of that, and it refers to autoregressive component. Very similar structure here. Theta of L is also the polynomial in lag operator. See, first term is multiplied by L to the power 0, which is by definition 1, right? 1. So L0, L, 1, L squared, and L to the power P. So this is polynomial in L, right? Up to Pth order. And this one all the way up to, let's say, Qth order. So this P, Q refers to that. Okay. So the simplest model suppose D is 0. That means you don't have to take first difference to make it stationary, right? So let's say D is 0. That means no first differencing required. So Y of T, and let's say P equals to 1. P equals to 1 there. That's pi of L, right? Mu is some parameter. Okay. And let's say Q equals to 1 as well. Q. Epsilon T way. Okay. Looks pretty much alien, right? So let's rewrite this one in more plain term. This polynomial can be distributed to y. So 1 times y is yt, right? Minus pi 1 times L times this, which is yt minus 1. Let's bring that term to the right-hand side of the equal sign. So pi 1, yt minus 1. Okay. Of course, there is a mu here. And here, epsilon. 1 times epsilon minus theta 1 epsilon t minus 1. So this model is ARIMA 101 model. 101 model. Okay. So again here, autoregressive feature here, right? Yt is explained by t minus 1. Okay. And this term defines moving average, where weight is minus theta 1. Okay. So if you rewrite this one by leading one period, so yt plus 1, yt, epsilon t plus 1, minus theta 1 epsilon t. Right? So that's moving average, right? Average between two adjacent disturbance terms, right? Okay, so the reason why we introduce this type of polynomial is to shorten this expression. Otherwise, it's going to be very lengthy, right, expression. So usually you write it this way, and then you can say pi of L and theta of L is defined this way. Okay. Now, these are the statistical definition of expectation and variance and covariance. Right? But when you calculate using Excel, for instance, when you calculate expected value of xt, do you actually integrate something from minus infinity to infinity? We don't do that, right? When you calculate average, we add them all and divide it by sample size, right? That's effectively, well, this is if you know the theoretical distribution of random variable x, which is f of x in this notation, then actually you can work this thing out to calculate expectation. Or if you calculate deviation from average squared and apply density function and integrate from here to there, then you get the variance. But usually what we do in practice is you calculate sample average and calculate this deviation as square, and then add them all and divide that by sample size minus 1, where minus 1 means you are using 1 degree of freedom to find this center. Right? So that's usually the way. So in time series context, let's see how to calculate those quantity in practice. What do we got here? Well, this one is a typical stationary time series. It's called P ratio, or price earnings ratio. So stock price and company's earnings, and it's believed that that figure is constant over time. So the way we model this one is in somehow, if we closely look at this sequence, there appears to be some average value and some sort of pattern. So several observations could be away from average or away from average, but it tends to return to mean, right? So what we'll do here is particular series like price earnings ratio. When we actually work out this exercise, it tends to be fitting very well if you model that one as this one instead of yt equals to that. Okay, so let's take a look at what we got below, and we come back to the forecasting of this P ratio. Okay, here we've seen that already. Autocovariance sample equivalent. So hat means it is computed using finite sample. The one without hat, that means population parameter. Okay. So if you have cap T observation, calculate average first, and then calculate deviation and cross product, add them all, divide by sample size. Of course, you can divide this one by one, multiply that one by 1 over t minus 1. But for some reason, it's known as the property of maximum likely estimation, where when sample size is really big, then it doesn't matter whether you divide something by t or t minus 1 when t is very, very big, right? So usually we use cap t instead of t minus 1. So this is the way we calculate sample autocovariance. And the name, well, is covariance between these observations, but we are looking at same x, right? So we use this notation, autocovariance. Are you comfortable with here in the notation subtracting x bar for this guy and x bar for that guy? Are you comfortable with that? Why is that? If x is stationary, then what is the expected value of xt? This one. What is the expected value of this one? The same, right? So you should feel comfortable with that calculation. We introduced correlation between these. And so if you calculate kth covariance using the sample and the sample variance, take the ratio, and that will give you sample autocovariance. So if you plug in this expression, the variance expression is basically the way we calculate rho of k using Excel. So this is the definition. The plot of autocorrelations against k. Here, in the previous slide, I had k and the rho of k, the vertical axis, right? And here we have different k's, and this is autocorrelations. Okay. When I actually used the Standard Poor's real stock return of a period like 1871 through 2003. Well, what is rho 1 hat? 0.049. 0.049. At second leg, minus 0.171. Some number, right? Some number. So at leg 1, is this number 0? Because you calculate this number using sample. It's a statistic, right? So you should have some band, confidence band. Right? What I'm saying is if you have rho 1 hat, calculate this one. Can we calculate variance of this one? So if this turns out to be, let's say, 0.10, let's make it simple. Let's say standard deviation of this statistic turns out to be 0.10. So usually when we make inference in statistics, we say if rho 1 hat minus 0, you're testing whether this quantity is in fact 0, right? You usually calculate this type of quantity. If this is in fact this big, But rho 1 turns out to be 0.049, very small number, right? So from this is 0 line, 2 times SD minus 2 times SD. Let's say this is the band. It turns out to be at k equals to 1, rho 1 was very small positive number lying within that interval, right? So we say there's no evidence that this quantity is different from 0. We say this one is statistically 0. Right? So to establish this, you need to calculate this quantity first. Okay? So we don't have it right here, but later I can show how to calculate this quantity. Loosely, this dotted line reported by EBUS, that's the boundary. Upper, lower. 2 standard deviation band. Okay. There's another one. It is called partial correlation. Partial correlation. Well, partial correlation probably is something we learned from time series class, not usual statistics class. The correlation is defined in a little funny way. See, you're calculating correlation between xt and t plus k. So k period apart, right? But here it is conditional. Condition. So calculating conditional correlation, and the condition is the information in between. So you are controlling the information in between, and in somehow you need to calculate correlation between these two. Okay? Well, previously we looked at correlation of annual S&P 500 stock return, but this time this is a price earnings ratio, the blue line I've seen. That one shows like autocorrelation appears to be, well, if we consider this dotted line as confidence band, it's lying above that region. So these are some non-zero quantities. Right? And also, if you look at this partial autocorrelation, there appears to be some non-zero observation. Right? Compared to stock return in real terms, so adjusted for inflation, nothing going on. Right? Okay. Then before I tell you how to calculate this one in practice, let me explain why we need these two versions of sample statistics. The following example will motivate you. Let's say y of t is generated from simple autoregressive model of order 1. Let's ignore sample mean, mu. Okay? Well, by looking at this model, two observations just one period apart. Two observations, are they related, correlated? Yes. Right? Correlated, if this is not 0, right? Pi 1 is not 0. Are these correlated? The simple question. Are they correlated? Yes. Answer is yes. Right? Let's say, how to see it? We lag this expression, one period, and plug in there. Okay? So let's do that. YT that way, right? So it is pi 1 squared yt minus 2 plus epsilon t plus pi 1 epsilon t minus 1. Right? So are they correlated? Yes. Right? Similarly, are yt and yt minus k correlated? Of course, right? So if these observations are correlated, this should happen, right? Suppose pi 1 happened to be, let's say, 0.9. So as k increases, the correlation, which is determined by this quantity, gets smaller and smaller, right? Pi 1 squared, cubed, and so on, gets smaller and smaller. So that's why this one decreases. Now, suppose you are given this information. You are given this information. What would be your potential autoregressive model for this time series? You have k and non-zero autocorrelations. Is there any clue about the value of k? Not really, right? Because you could have model like this one. I'm just making it up. Let's say other parameter psi this model also have correlation non-zero if this is non-zero, right? And for this model, this could be non-zero, right? Correlation could be non-zero. So should I pick this model or that model or something else? So autocorrelation appears to be telling you that y is in somehow related to previous observations, right? But that's all it says, no more. But when you actually try to build model like autoregressive model, you want to know what would be p, right? P. So partial autocorrelation now come into play, which is defined as conditional expectation. So the trick is how to actually do this, conditioning something. Right? But that's very easy one. But before I get to this part, also we have very funny notation for partial autocorrelation. Autocorrelation, we use Greek rho, right? Notation rho. But here we have pi and k, not single k. But you can see easily why is that. Pi kk, let's say k equals to 1. K equals to 1. Then mu1, pi 1, 1, xt minus 1, and no more, right? When k equals to 1. So 1, 1 coefficient is this one, right? 1, 1 coefficient. So that's the first value here, when k equals to 1. When k equals 2, you have 2 legs, right? So 2, 1, 2, 2, that coefficient. So when you actually did that, you want to calculate correlation between x and t minus 2, xt minus 2, while you control this one as conditioning information. So that's the way we treat conditional statement in terms of regression. Okay. When we actually go to those workshops and presentations, suppose that someone provides the evidence about, let's say, good governance of company tends to lead company more profitable. So if you don't think Samsung Electronics has good governance, then if that theory is correct, then they will have less profit. Some social company, their profit, as that regression, if that's correct, then that kind of argument could be brought by running a regression, right? So in somehow you need to measure whether a particular company has a good governance or bad governance or in between, right? So that's explanatory variable. And that company's earnings, perhaps scaled by asset size, that could be a dependent variable. So run a regression, right? And if that is positive, then you say, well, good governance tends to lead, more profitable situation. Because many, the public could be favoring those company who has better governance structure. That could be kind of story. But whenever you bring that kind of output, then probably the first question you hear from the audience is that, did you control for such and such? Well, the company's earning is not solely determined by the governance structure. There are many other factors, right? So in econometrics, the first lesson probably you learn right after learning how to estimate this coefficient is that, well, you better include more variable than is enough. Otherwise, you'll have omission error, which is very critical. So suppose you need other independent variables, but you leave that out and estimate simple model, then those all other left out variable will enter here. And without considering actual structure of this one, if you just simply estimate this quantity using this regression, sometimes the sign of this parameter could be reversed depending upon the effects of these omitted variables, right? So the safer bet is to include more and more variables. It won't hurt you. You will lose a little bit of accuracy, or we say efficiency, but no critical bias will occur when you apply least square method. So the conditioning set is included, okay? And here, when you try to calculate pi k, all those in between observations are included, right? That's conditioning. Right? So this is the least square is very simple, easy. Just easy to compute. So if you run this equation recursively and keep track pi 1, 1 through pi k, that gives you this quantity. Long time ago, when we don't have any personal computers, of course, statistician, time series economist Durbin, when they worked out this kind of theory, they didn't have any personal computers, so they devised something recursive formula to calculate this pi k. But we can show theoretically that whether you compute using old-fashioned way or new way, you have same statistical property. So these days we do just simply least square several times to get this partial autocorrelation. Okay, now what is then the use of this partial autocorrelation? What's the meaning of this one, non-zero? Clue is here. Think about what is the meaning of having non-zero partial autocorrelation at leg 1. Answer is by looking closely this one. You see? Suppose true model that generates this data is AR1, autoregressive model of order 1. Then if you calculate pi 1, 1 using that data, will that be 0 or not? Non-zero, right? Okay. Suppose true data, same, autoregressive process of order 1. Suppose that's a true model. Suppose you computed pi 2, 2. Will that be 0? Truth is AR1 process, but you are running a regression not only the leg 1 variable, also the second leg. So will this coefficient 0 or not? 0, right? So this information appears to be telling us that, well, if you keep looking at this value up to non-zero, it will probably tell you what is the appropriate value for P. The order of autoregressive process. So if the data is generated by, let's say, ARP, pth order autoregressive process, then partial autocorrelation will be non-zero up to k equals to p, and then statistically 0. So in this case, the first one appears to be non-zero, and then statistically 0, right? So this appears to be suggesting that the underlying series is AR1 process. Even if it is AR1 process, we know that this has to be the case, right? This has to be the case. Yeah, because of this, right? So by looking at this, we don't know. We don't have any clue about this information. But if you look at partial autocorrelation and the cutoff point, then that will tell you what is appropriate value for P. Okay. Actually, sometimes if you work with different sequence, and suppose partial autocorrelation is slowly declining like that, like this one, and autocorrelation could be like this one, cut off. So the opposite situation. But in that case, if autocorrelation cuts off after certain lag, let's say lag 1, like this one, then that's the indication of Q, the moving average part. Exactly the opposite way. It works the opposite way. So cutoff point is checked from partial autocorrelation, and that is to determine P. And if there is a slow decay in this area and cutoff in autocorrelation, then that's the indication of moving average process with Q as an order. But if you try to remember two at the same time, usually the outcome is all incorrect, right? So just remember one case, and the other is the other way around, right? So use partial autocorrelation to determine the order of autoregressive process. Okay. So it will cut off after certain lag, right? So because at lag 2 it is 0, so in this case AR1 process is your best guess for price earnings ratio. Okay. Now here comes the standard deviation. Actually, the calculation is a little messy. We'll just take a look at the result only here. Suppose that you want to calculate the variance of sample autocorrelation at lag k. This is approximately 1 over t and this one. And here, counter j run from 1 through q. 1 through q. So if q is 0, and this one starts from 1, right? Counter doesn't go from 1 to 0. It always increases. So if it is q is 0, then this one is not relevant. So 1 over t is the answer when q is 0. When q is 1, 1 through 1, row 1, right? So the story is like this. Suppose you are testing whether original sequence is just random series, no correlation. If that is your hypothesis, then set q equals to 0 and compute this one. So if your observation is 100, then 1 over 100 is your variance. Take the square root of that to calculate standard deviation. So 2 standard deviation band could be constructed from 0 here and minus 2 times standard deviation, which is square root of this one, right? So testing whether sequence is purely random, case of q equals to 0, standard deviation of row k is 1 over square root t. SD rho k hat is approximately 1 over square root t, right? Suppose when you actually test that, suppose you rejected null hypothesis. So there is a serial correlation. Then you start to move from 0 to 1. So 1. So you're testing whether, let's say, first serial correlation is non-zero, but rest of them 0. Because you already rejected random sequence, hypothesis of random sequence. So there is at least one serial correlation, right? So first serial correlation is computed some non-zero number here, right? So you plug that in here. So 1 plus 2 times rho 1 hat squared times 1 over sample size. That will give you rho 1 hat, rho 1. And still you find the still you find more serial correlation other than lag 1, then you can keep going 1 through 1 to 2, 1 to 3, 1 to 4, and so on. So a band is usually increasing like this. But here, we're talking about this band. So if this is non-zero, then to calculate standard consensus band for the second one is not the same as the one you calculated previously. Because 1 plus 2 times the summation, that quantity, it will usually make this thing blow. Okay? But I don't know why people do that, but many people these days just calculate just this one, which is 0 plus minus 2 times. So you know this one, right? This is standard deviation of rho, right? When Q is 0, right? Right? And just stop. So it's acceptable process. But how about this one? The same quantity, this one. It is known that the standard deviation or the variance of partial correlation is always 1 over t, regardless of k, value of k. But this one says the variance of rho k will depend upon the value of k. This approximation was computed by time series econometrician Bartlett. So this is what we call a Bartlett's approximation. Okay, let me show you this part and as a last subject. Well, in many of the studies in the field of finance, something called small sample bias plays important role. Because as I said, stock returns vary over time, but little is explained by previous information. So most of the variation is simply due to the news, information inflow to the stock market, which is not predictable. Okay? But if you run a regression, sometimes people find a small but still non-zero correlation in particular regression. But those regressions, there are many critical situations where you can easily misled by small sample bias. So one of the examples here is, let's say X is uncorrelated time series with mean and the variance 0 and sigma squared. Constant mean, constant variance. Because this is uncorrelated series, if you calculate rho hat K using X, then the expected value of that has to be 0 for every K. Right? So when someone actually calculated this one, theoretically, they found this expression. Don't worry about this part. There is a notation, what we call order of magnitude, big O, little o. But when you see this little o, you can think of that as something that converges to 0. When you see this big O, that means that converts to some small number, a small number of that much not much significance. Okay. So what it says is, if you actually calculate rho of K using finite sample, and if you take the average of that, so you have a random sample, X, set of X, calculate rows. Each time you have little different numbers, right? But on average, that has to be 0, right? But the expression says this number. T is sample size, K is the lag. So row 1 cancels. So minus 1 over T. So if you are working with 10 observations, then if you calculate row 1 hat, expected value is minus 1 over 10, which is 0.1, minus 0.1. That's downward bias. Right? So if you are working with small sample, you are more likely to find negative number, even if the true data generating process is random. Okay? So we need to somehow deal with this problem. So practical consequence could be like, suppose you have stock return, which is uncorrelated. But if you just pick small sample of stock returns, run a regression of xt on t minus 1, you are likely to find what? Negative correlation because of downward bias, which is serious, right? Situation. So, of course, if there is a problem, then we have a remedy for the problem as well. So we'll get to that part later. Okay, better stop here. When I come back later this week, we'll start talking more about the properties of those autoregressive model, moving average model, and try to build our first forecasting model for GDP. Okay. Questions?